All right. Well, hello all and welcome. Start off by making everyone aware today's session is being recorded. This recording will be shared with all registered attendees and will be available on New York Sea Grant's Seaweed Food Safety resource page, which will be linked on the slides as we go through today and also shared post meeting. My name is Mike Ciaramella. For those who don't know, I'm the Seafood Safety and Technology Specialist with New York Sea Grant and Cornell Cooperative Extension. I'm currently leading a USDA food safety outreach program funded project to develop a hazards and controls guide to support safe seaweed production and marketing. For today's session, I'm going to start with a brief introduction and update on the project itself, especially for those who are joining us for the first time, before we move on, more specifically looking at the chemical hazards associated with seaweed and seaweed products that our team has identified through this effort. So first, I want to remind everyone of the purpose of the project in general and the guidance document that's being developed. Ideally, it's meant to assist the industry as well as agencies in assessing and mitigating risks associated with seaweeds that are destined for human consumption, specifically in US markets, because it's tailored to support the development of food safety plans or HACCP plans as regulated or required by the federal and state regulatory officials. It's also going to ultimately serve as the foundation for a seaweed-specific food safety training that a group of colleagues across the nation, as well as some international participants, have been exploring to better support the emerging seaweed sectors across the US in complying with prevailing food safety regulations as they pertain specifically to seaweeds and seaweed products. So for our project, we started with our outline of the document itself and assigning of chapters through our core team. It's largely based off of the seafood or fish and fishery products hazards and controls guide. We then worked to identify appropriate literature, draft out those chapters, coming to consensus on the recommendations, hazards, and some options for control to provide that clarity and guidance. We then had internal review of all those documents among our core team and authors before we sent that out for external review. We had 30 external reviewers invited. We received 15 reviews, and we incorporated and worked through final revisions of each of the chapters on the various hazards to address the various comments that we received through that external review process. We're now in that final stage you see here of a copy editing, formatting, and final making the document ready for public viewing and that artwork. So in these final steps, we're working with a graphic artist to do some cover art and develop some illustrations to complement some of the content in that guide. We're also having 2 infographics developed as standalone resources, but complementing some of the information that is in the guide itself. We're finalizing the format and copy editing to ensure consistency in tone and format throughout the guide, ultimately with the goal of publishing and having this readily available in September of this year. So just in a couple of months, we're hoping to have this available for use. As I said earlier, all these resources are going to be posted and available through the website, that URL you see in the bottom left, newyorkseagrant.org/seaweed guides. We also, through this effort, are hosting a series of webinars. This is the 3rd and final webinar in that series. We started with a regulations webinar overviewing where seaweeds fits within prevailing federal regulatory framework. That one is already available on that resource page. We then had a biological hazards, a webinar that focused on the various biological or microbial hazards associated with seaweeds and seaweed products. And today, our 3rd and final webinar will focus on the various chemical hazards that we've identified as potential or associated with various seaweed products. Also, before we jump in, noting that this is meant not for domestic seaweeds only. This is meant for all seaweeds in the US market, right? So it's pretty inclusive of any seaweeds that are identified as being used for human consumption, to ensure that we are covering all the potential products that could be on the market here in the US. All right, so now we'll focus more on our chemical hazards. So I'm going to be starting off with presenting some of the chapters and some of the hazards that I worked closely on. And then Dr. Razieh Farzad is going to be joining, and she's going to take over for some of the other environmental chemical hazards. Dr. Christina DeWitt is one of the other key authors on our environmental chemical chapters today, who's here to help answer questions, but not officially presenting at this time. So as far as the hazards that we're going to cover on today's webinar, we'll start with iodine. We'll look at natural toxins. We'll cover some allergens and food intolerant substances, and then finally end on a larger topic of just general environmental chemical contaminants that are or have been associated with seaweed and seaweed products. So to kick us off with iodine, so we want to know what's the deal with iodine, right? We hear a lot about iodine and there's been many concerns about iodine in seaweed, but ultimately we know that iodine is crucial for making thyroid hormones that ultimately regulate vital body functions. And so it's an important part of our diet. Back in the 20th century, there was widespread iodine deficiency, which ultimately led to the development of voluntary salt iodization programs to increase iodine consumption in the American population. So iodine deficiency was believed to be an issue of the past. However, more recent data is beginning to suggest that decreased consumption of iodine salt across the US is ultimately potentially resulting in increased deficiencies in iodine. So there's opportunity here for seaweed to supplement that. However, there's known risks with overconsumption of iodine that we're aware of. And seaweeds in some cases can have extremely high levels of iodine. So that's why there was this question of whether or not iodine is actually a risk and something that needs to be controlled versus a good benefit to consuming seaweeds. And that's what we tried to explore through the development of this particular chapter. So the first thing we wanted to take a look at is, well, what's recommended intake of iodine on a daily basis for the average American, right? And also, what are those upper tolerable limits? When do we start seeing potential negative or adverse impacts of consumption with higher concentrations? So this is information that's available through the National Institute of Health, and it is the recommended daily intakes, or RDIs, on the left-hand table. And you'll see that RDI changes based on life stage or the age range of the individuals consuming it. It's a higher RDI for those younger because of the importance of iodine in fetal development and child development. And then it increases, and then it decreases, and then increases again as you go into adulthood, where the average adult is typically recommended to consume 150 micrograms of iodine daily. That's higher for pregnant and breastfeeding women, ultimately, again, because of its role in fetal development and the importance there, right? But too much of a good thing is not always great. You can see there's upper limits that are published for iodine at the various life stages that range anywhere from 200 micrograms daily to 1,100 micrograms daily for the average adult 18 and older. So now we know kind of what are the normal or healthy ranges for consumption that we're looking to achieve in our products. And now we want to take a closer look at what's the actual concentrations of iodine in various seaweeds and seaweed products. So the data we're showing here is just iodine concentration ranges that were pulled from the literature, anybody reporting iodine concentration in seaweeds. And you can see that there's quite a lot of variation, both within the type, green, reds, and browns, but also between the different types of seaweed. In a green seaweed, you'll see anywhere from 13 to 154 micrograms per gram of seaweed. Red seaweeds is 4 to 353 micrograms per gram, and browns are 12 to 10,203 micrograms per gram, right? So you see the lowest in greens, then our reds, and highest concentrations are typically observed in our brown algae. We also need to then consider serving size. The typical serving size for seaweed is 5 grams. So if we have the iodine content reported in micrograms per gram, we multiply that by 5 and we can see how much iodine would be present in a single serving for these different types. And it ranges from 65 to 770 micrograms for greens, 20 to 1700 for reds, and 60 to 51,000 micrograms for brown. So you can see we're clearly exceeding those upper limits in many cases in many of these seaweed products. So it's important to take that into consideration when you're evaluating your product and ensuring to protect public health and ensure consumers who may have negative impacts upon consuming high levels of iodine in their diet. This is especially important for individuals who have existing thyroid issues and are hypersensitive to iodine in the diet, right? And so best is to have ways for them to avoid and understand what's present in these foods that could negatively or adversely impact their health. So based on that, we developed some control strategy or how industry could implement strategies to prevent any adverse health effects associated with iodines in seaweeds. So the two control strategies ultimately being processing control. So there is evidence showing that you can reduce the concentration of iodine through various processing methods. To date, there aren't necessarily validated methods that everyone can apply and use, right? But there's lots of information out there on various methods that have been used that have had success in reducing iodine content. And then obviously the best control here is just labeling and making sure that consumers are aware that there are high iodine concentrations in this product. Ideally, what is that iodine concentration? So it really helps them make a decision that's best for them and their dietary needs to avoid products that may be adversely affecting their health. So in summary, when it comes to iodine, iodine can be considered a significant hazard or a known, reasonably foreseeable, or reasonably likely to occur hazard when those concentrations in a single serving exceed the daily upper limit. So ways you can control this, one, we mentioned processing to remove iodine, but it's important to note in processing to remove, right, especially in those seaweeds where you're seeing those extremely high concentrations. So in that brown seaweed at the high end or the extreme with 50,000 micrograms, that's 50 times the daily upper limit. Even if you can reduce through processing 50, 60, 70%, right, you're still likely exceeding that daily upper limit. And so that alone may not be an effective control for that particular product, right? And so there are other things you can consider, such as changing the serving size. So instead of developing a product or a value-added product out of that seaweed that has that 5-gram serving, but reducing that, spices, mixes, seasonings, where you're reducing the serving size, thus further limiting exposure to those higher concentrations. And then ultimately labeling that product so that the consumer is aware that that's a high iodine containing product and they can avoid that if necessary for those who do have those existing thyroid issues where they could see negative or adverse effects upon consumption. So I'll transition now and we'll look a little bit more about natural toxins, right? The second chemical hazard that we've identified as potential for various seaweed and seaweed products that have been identified in a variety of different seaweeds. So natural toxins or naturally occurring toxins have been detected in or on several seaweed species. They're typically resulting from seaweeds themselves that are producing the toxin, typically in response to stress or predation. There are instances where there are epiphytes living on those seaweeds that actually produce the toxins and thus make those seaweeds potentially unsafe. Or there could be instances where the toxins are readily present in those growing waters and ultimately can contaminate those seaweeds upon harvest if not controlled. When it comes to specific natural toxins that we're concerned about, there were several that we've identified through our research that have been associated with seaweeds. You'll note here I have this asterisk. This asterisk indicates ones that were specifically linked to poisoning or intoxication from seaweeds. The two that are not, do not have the asterisk were detected and identified as present in various seaweed products, but have not to date, or there's no record of them directly being linked to a seaweed intoxication or poison. So the first here, neurotoxic amino acids are toxins that are commonly produced by certain marine organisms, typically microalgae. Examples being domoic acid, cyanuric acid. Domoic acid, many may be familiar with, that it causes amnesic shellfish poisoning or ASP, which is commonly associated with marine waters and shellfish growing areas. Both of these have been detected in macroalgae species, again, although neither have been linked directly to intoxication after consumption of seaweed and seaweed products. The next on here is diethyl peroxide. It has been identified as the suspected toxin that's responsible for mozuku poisoning. There's been 2 documented cases of mozuku poisoning in Japan, and this toxin has been detected in several seaweed species. It's also important to note that for this one in particular, the toxin is actually formed when that product is heated. So it's not actually present in those raw seaweeds. It's formed in that processing or cooking process. Next on here, we have caulerpin or caulerpicin, right? This is a chemical compound or chemical compounds believed to be associated with the peppery taste that is sometimes associated with the green algae caulerpa or caulerpa species. And while these compounds are often referred to as the toxic elements, there is some contradictory research out there indicating that these are not actually what's creating that reaction or that toxic element within that species. And although there's not consensus on what's actually the toxic compound in the caulerpa species, it's not is agreement that Caulerpa species in general tend to produce some sort of toxic effect and have can negatively impact upon consumption. Next is prostaglandin E2 or PGE2. This is believed to be the causative agent in ogonori poisoning, which is believed to be produced when the seaweed is stressed by environmental conditions or predation. This has most commonly been associated with various Gracilaria species. And it is the only of these toxins that we've found any evidence in the literature to suggest that it could potentially be controlled through processing. So potentially heat treatments to destroy or remove that toxin. Most of the other toxins tend to be heat stable, and there's very little indication that they can be controlled once present. Aplysia toxin and dibromoaplysia toxin are toxic alkaloids that are produced by marine cyanobacteria, so blue-green algae. These cyanobacteria are known to grow as epiphytes on marine seaweeds and thus produce toxins on those products, which have been implicated in foodborne poisoning, specifically in this case in Hawaii. The next is polycarbonicide A, which is a toxic compound that's been isolated from Gracilaria edulis, was the only species we were able to find that being isolated from, and it was directly linked to 2 outbreaks in Guam and the Philippines. And lastly on here, we have mycotoxins. So there are certain foods that can harbor fungi and molds and produce toxic compounds known as mycotoxins. These are typically associated with dry foods. However, studies have detected mycotoxins on raw seaweeds. In those cases, these levels have been below those of concern, and this has never really been associated with intoxication or any poisoning events. Ooh. So when it comes, what's going on? When it comes to assessing the risks associated with these various natural toxins and determining whether or not they're actually significant, again, this guide has all of these potential toxins because they've been associated with seaweeds, but just because it's noted in the guide does not mean it's significant for every individual, every species, every operation. So producers should really assess the risk of these toxins being significant, which is a known or reasonably foreseeable or reasonably likely to occur hazard by historical occurrence in the growing waters, known contamination or presence of that toxin at the time of harvest in those growing waters, or species that are specifically associated with the production or presence of that toxin. And when it comes to controlling them, the best control for natural toxins is going to be your source control, right? Not sourcing products that are inherently toxic, not sourcing products that are from water bodies where there are toxins present, especially when it's known that that toxin can contaminate that product. The other potential option that we do note in the guide, but try to indicate very clearly that this is a very limited application is processing control. As I mentioned earlier, we've seen some evidence for some of those toxins where there could be processing controls that can remove or mitigate that hazard. In many cases, this does not exist for most of these toxins, right? So and there are no validated studies currently available that will give you the appropriate methods for controlling various toxins with processing techniques. So those would need to be taken on and done by anybody looking to use processing as a potential control. So in summary, natural toxins can be considered significant when those seaweeds are known to produce such toxins naturally or harvested from waters with those toxins. Processing potentially has applications for removal and control of this, but it's a very limited application. PGE2, again, was the only toxin where we could see in the literature where there was potentially an option for processing to remove that hazard. But further research and validated studies would need to be conducted to effectively utilize that as a control. So the best control for these natural toxins is going to be to source your product from waters that are not contaminated and look for seaweed species that are not readily associated with toxins and toxin production. So the last hazard that I'm going to cover is going to be allergens and food intolerant substances. So when it comes to allergens, we know there are 9 major food allergens in the US, and a major food allergen gets that title by contributing to 90% of severe allergic reactions in the United States. And if you look at FDA's wheel of major food allergens here, you'll see that seaweed is not on the list. Seaweed is not in and of itself a major food allergen. The only aquatic foods you see on this list are going to be our fish and our crustacean shellfish species. The other hazard we are covering here is looking at food intolerant substances. So there are various food additives that are food intolerant substances. Commonly we see, especially in seafood, those sulfites and then artificial dyes or colorings. There's not a lot of evidence that these are readily used in the seaweed industry at the moment that we could find. But if they are used, there is need to control for that. So we do include them here in this guide. So let's revisit this topic of allergens. As I said, seaweed itself is not a major food allergen. However, crustaceans are, and we readily see small crustaceans such as shrimp like amphipods on harvested seaweed products and growing and living within the seaweeds in that marine or aquatic environment. There's lots of evidence out there showing that this crustacean allergenic protein, tropomyosin, can be detected in various seaweeds and seaweed products. However, to date, there's been no allergic reactions specifically to crustaceans that have been linked to seaweed directly. Right? So when it comes to assessing, well, is this a significant hazard for our seaweed products? Ultimately, we'll note that labeling of crustacean allergens on seaweed products is not a requirement, right? There's no requirement to label it as an allergen. But producers should be wary and assess the risk based on the recurrence or recurring presence of crustaceans in or on that product. So the presence of these crustaceans can vary. It can be seasonally, it can be geography, it can be different growing waters. And if you regularly are seeing high levels of infestation of these various crustacean species on that product, it may be good to consider that a significant hazard, right? And implement a control strategy to prevent that from creating or causing any kind of allergic reaction. A great way to assess risk over time, especially, is to monitor consumer complaints and follow up on consumer complaints. If you're seeing consumers complaining a lot about having an allergic reaction, follow up with them. Find out if they have an allergy to crustaceans. If you're regularly seeing allergic reactions in consumers that tend to be allergic to crustacean shellfish, that may be indication that you have high levels of this tropomyosin that is resulting in allergic reaction, thus warranting further control and implementation of HACCP or preventive control within your food safety plan. So food intolerant substances, again, these are substances like the sulfites and dyes. When they are used, they should be properly labeled. If they are used in a product, it must be controlled. Again, we didn't find much evidence of these being used readily in many seaweed products. However, there was a study looking at a lot of different microalgae species on the market that did have quite a lot of sulfites associated with that. So if you're considering any of these food intolerant substances, again, that would be a significant hazard that warrants a control. All right, so control strategies for our allergens and food intolerant substances. So the first one we have on here, note, and this one's a little bit unique. We have a source control strategy that the team is going to be exploring a little bit more. But because of the nature of this particular hazard and the fact that the seaweed itself is not the allergen, but it's the presence of those crustaceans on or in that product that's resulting in that allergen, there's potentially opportunity to source product, one that has low infestation, right? That comes from an area that doesn't have an issue with crustacean epiphytes, or to have practices in place at the farm, such as rinsing, washing, manual removal, or harvest times, right, that coincide with or prior to the heavier infestations by these to help you control that potential allergen. So that's why source control, not typically something you would see as an allergen control strategy, but we are exploring it here in the guide as a potential option to reduce the likelihood of those allergens being present. Then there's the obvious labeling control. If you have an allergen or may have an allergen in that product, you can label that product as such so consumers are aware to avoid that product if they're highly sensitive or allergic to that. And finally, we have that sanitation control strategy in here, noting that this is specifically a requirement within a preventive controls food safety plan, but also part of a prerequisite program typically in HACCP. But we do provide the examples and example controls, preventive controls for these in the guide, because this is meant to serve as a resource for those operating under preventive controls as well as HACCP. Right, so that sanitation control really more applying to instances where you have multiple allergens within a facility. So trying to accommodate all scenarios where someone might be processing and utilizing seaweed within their facility. All right, so in summary, when it comes to allergens and food intolerant substances, When seaweed is regularly associated with crustacean epiphytes and you see heavy infestation on a regular basis, that product can contain that allergenic crustacean protein and potentially cause allergic reaction, warranting a control within your food safety plan. When food intolerant substances are used in products, anytime they're considered significant hazard and should be controlled. The controlling strategies, product sourcing, again, unique in this scenario because it's not the product itself that's inherently the allergen. There can be ways where you can implement controls, maybe at the farm level or some maybe even processing level for reducing the likelihood. There's the labeling control, and there's two options with labeling. We have the direct allergen statement, simply stating that there are crustacean allergen is present in this product, and anyone allergic should avoid the product. There's also the option to use that may contain statement, and that may contain statement, while valuable and can be used, it cannot be used in lieu of any other additional sanitation or best management practices that are aimed towards reducing the likelihood or presence of that allergen in that product. So if you're going to use that may contain statement, it's essentially saying that, well, we don't think there's anything here, but it may be there because of the nature of this product. You should be doing what you can to minimize any risk of that allergen in that case. Whereas the allergen statement, you're simply stating it's in the product. Avoid if you're allergic. Sanitation practices is, again, to reduce the presence of allergenic proteins, and this can be the crustacean allergen, or depending on what your product is, your final product, any other allergens within your facility. Sanitation preventive controls may need to be in place to ensure you're not or creating an instance of cross contact where different allergens can get on the final products you're producing. So with that, I will pass the screen over to Dr. Farzad to cover our environmental chemical hazards.
Thank you, Mike. And good afternoon, everyone. Very great to see all of your names on the screen. I see a couple of familiar faces. Hopefully, people can see my screen. As Mike said, my name is Razieh Farzad. I'm an assistant professor at University of Florida, and I'm also the Seafood Safety Extension Specialist with Florida Sea Grant. I worked on writing the chapter 7 of the guide that Mike gave an introduction about, focused on environmental chemical contaminants. Other co-author of this chapter are Dr. Christina DeWitt, Mike, and myself. And before I get started, I wanted to thank all of our external reviewers. We basically rewrote the whole chapter based on their comments, and we couldn't have done it without their help. So let's jump into the chapter. Some of this is the repeat of what Mike said about the project itself, but I think it's important to give some introduction about this chapter because whenever our guide is available, it's going to help you understanding why we laid out the chapter the way it is. So as Mike said, most of our seaweed is imported. We hope that most of our local farmers are going to produce this guide, but the reality is most of the seaweed available in the United States market are imported. So this is developed for both domestic and imported product. And you see many data for international species that they have been evaluated for environmental chemical. This applies to both wild and farm-raised type of seaweed. We understand that the method of production, the environmental factor, all of those things might affect the environmental chemical contaminants, but the guide has laid out in a general way that you can all use it and decide based on your specific situation if environmental chemical contaminants are providing risk from your product. And when we went back and look at all the regulatory standards around seaweed, we understand that those standards are limited, but we had to rely on available standards. So if there are any standards relevant to seaweed, we have provided it in the guide, but in many cases it wasn't available. So we provided the food safety standards that are available and can be applicable to seaweed. I have provided some of those numbers on my slides. I'm not going to read through them, but it's just for your information. So The environmental chemicals, contaminants that we covered in this chapter were heavy metals, pesticides, radionucleotides, and persistent organic pollutants. And I kind of want to emphasize that, like bivalves, seaweed can accumulate these certain chemicals. They are providing this ecosystem services. They are good biomonitors, but at the same time, this is a double-edged sword. Because they are accumulating these chemicals, they can cause food safety concern. So what are heavy metals? Heavy metals are naturally occurring elements with a density of 5 grams per square centimeter or greater. I want to emphasize that not all heavy metals are toxic, but there are some of them are even essential, but there are some that have shown associated high risk with negative health effect, even at low concentration. There are many factors that can affect the heavy metal absorption by seaweed and consequently the toxicity by consumption. Different species that absorb these chemical heavy metals in a different amount. The morphology of seaweed can affect that. If they have a higher surface area, they absorb more heavy metal. Blade section that the sample has been taken can affect the amount of heavy metal. Older or basal sections of the blade may accumulate more heavy metals. Environmental conditions such as salinity, pH, water temperature, water current, and light can affect the concentration as well. Whether how long you are close to the source of pollution can affect that as well. And also season and growth depth. Contaminant levels vary with the season and the depth that the seaweed has been cultivated. To add to the complexity, the way that many things can affect other things that can affect the absorption and toxicity is the chemical form of this heavy metal. So some of these heavy metals that I'm going to give some example, they have inorganic and organic forms, that some are toxic than the other form. Dose and frequency matter. Regular consumption of contaminated seaweed obviously can result in chronic exposure and risk. Individual sensitivity, so age, genetics, nutritional status, and health condition can affect toxic response, and processing and cooking. So cooking at home or processing might decrease or increase the heavy metal. So I'm telling you all of this to show that it's really complicated, and it should get evaluated case by case whenever you are processing seaweed to see if a specific heavy metal is a concern for your specific product. So that being said, what are the heavy metals that we covered in this chapter? We mainly focused on 4 heavy metals: arsenic, cadmium, mercury, and lead. The reason that we chose these and we decided to move forward with these 4 heavy metals is that they have proven recognized negative health effect. The European Food Safety Authority identified them as major contaminant in seaweed, and World Health Organization includes them among the 10 contaminants of public health concern. In US, even though they don't specifically talk about seaweed, but they are considered toxic heavy metal that should be evaluated in seafood food supply chain. I said all of those things. There are other metals that can accumulate in seaweed and cause toxicity. We didn't mention them in the guide. Going back to the topic that this can be very specific, it's your responsibility to look at those specific metals such as aluminum that was in the literature a little bit to see if it's relevant to your case. Okay. Let's look at some information about some of these heavy metals. So arsenic is inorganic and inorganic form. The inorganic form of arsenic, such as arsenate, is highly toxic. The reason for that is because they can replace some of the elements in our body cells, as cells cannot communicate to each other. They use them for chemotherapy, they are very helpful, but when we eat them, is not good for healthy cells. And we have organic forms such as arsenosugars. Majority of the arsenic that I found in seaweed is arsenosugars. They have lower toxicity, but they are bioavailable to human, and some of their metabolites can be toxic. In some species of seaweed, total arsenic can exceed 100 milligram per kilogram. Brown seaweed, such as hejiki and kombu, can contain higher level. And the literature that we look at shows that there are elevated levels of inorganic arsenic in Laminaria species, and they highly suggest that for monitoring for that specific species, for inorganic arsenic. So in the guide, we have provided some of the safety limits that exist by European Union or other countries. But as you can see here, I have provided the provisional total weekly intake, which is the amount that you can take daily per week to stay healthy without causing any health to you throughout your lifespan. And this is usually mentioned as milligram per kilogram of body weight per week. The reason that we included that in the guide is that this might help you calculate if the amount of heavy metal in your product is toxic or not. We didn't provide any calculation because it's very complex and it can cause confusion, but the numbers are there. And you can use California Prop 65 safe harbor levels that are basically thresholds for chemical exposure, below which the businesses are required to provide warning. And NSRL is no significant risk level, and these are the numbers that have been provided for arsenic. What about cadmium? Cadmium was another heavy metal. As I said, they are highly toxic to kidney. They are associated with cancer and neurotoxicity. They have been found at a higher level in red and brown seaweed. And they are very site-specific, and they have been detected in the level US cultivated seaweed that are below the French limit, which is a very old regulation. So I think that number might be a little high. And monitoring is essential, particularly when you are near urban estuaries or wastewater impacted site. So again, these are numbers for mercury. I have one cadmium, one interesting example that FDA actually went ahead. We didn't include it in the guide because it was a specific product. They looked at this PTWI, and they looked at the specific seaweed product, and based on their evaluation, they suggested that that specific seaweed is risky for children under 6, and they suggested to look at the dose and maybe calculate things based on those PTWI and address this for labeling. Again, we haven't included in the guidance because this can get complicated, but case by case basis, you can use the calculation to prove that your product is safe. Other regulation available are from the very old French regulation, EU, Taiwan, and California Prop 65. Mercury, which is very toxic neurotoxin, especially for children, typically found at low concentration in seaweed compared to seafood. And we are mostly concerned about methyl mercury, not the total mercury. Total mercury in seaweed often range from 0.2 to 0.055 milligram per kilogram. For all of these things, including arsenic, speciation data is limited, meaning that most of the research that we look at, they look at the total amount of arsenic. They don't look at what are the forms that are available. The same with mercury. The speciation data is limited. They usually report the total mercury, which is not a good number for evaluating the risk. We have seen some site-specific variation, and the level can be obviously influenced by proximity to industrial discharge. Based on the literature that we saw in the United States, the mercury cannot, at the time, is not a major concern, but we need to continue monitoring. There are some available safety limits for mercury as well. In US, EPA and FDA have some action level for seafood, which is 1 ppm or 1 milligram per kilogram. Again, this is typically used for fish, not seaweed, but it's referenced in the risk assessment. Lead is a neurotoxic, especially harmful to children, and it can cause some irreversible development of damage. Brown algae tend to accumulate more than red or green varieties. Again, this is very site-specific and monitoring recommendation for products that are harvested near urban or historically contaminated sites. There are some available, the only available safety limits is from France, which is very high. That was one of the comments from the external reviewer. And I had to go back and check, but that's the actual number. I assume many of these numbers are going to get updated. Okay, there was one study from Europe that they did a risk assessment, hazards ranking based on 4 criteria. They looked at potential health effect on human, potential health effect on animal, frequency of reporting to the EU rapid alert system, and their stakeholder concerns. And they prepared this scoring, and based on this scoring, they assigned moderate, major, minor, or major ranking for these heavy metals. Based on their evaluation, mercury and lead has moderate ranking, and cadmium and arsenic, they had major ranking. We don't have such ranking in the US, so we rely only on you looking at your species of interest, looking at the location that the product is being harvested, and historical data. Okay, moving on to pesticide. I noticed that I have so many other slides, so I'm going to just fly through this. Another environmental chemicals are pesticides that can cause marine contamination. The definition is organocorrolines, organophosphates, carbamates, paratoids, and biological agents. Their entry route is either through agricultural runoff or aquaculture use. If they are, anything is getting used for disease and pest control. And there are some modern versus legacy pesticides that are more water soluble and less persistent. The legacy pesticides, we are not allowed to use them anymore, but they are highly persistent, and we still find them in sediments and biota. So factors that can affect pesticide accumulation in seaweed include their morphology. If they have a rough texture, they might trap and suspend the particles. The one that they have longer life cycle, obviously they can accumulate more. Lipid content, higher fat species can absorb more, and even though the one that are not very high fat content, they absorb pesticide as well, and their location in water column affect as well. Proximity to the sediments can increase the risk. So there are seasonal patterns and persistence. They peak during fruiting season due to increase in fatty acid synthesis, and the structure changes that can enhance the particle contact. And organochlorines persist like PAHS and PCPS. I have put the actual acronym spelling out at the slides. They accumulate in the sediments and suspended particulate matters. Okay. Moving to global monitoring and some site-specific risk, the survey results has shown that most pesticide residues are below maximum residual limits. There are some exceptions, elevated organochlorine levels in area with historical pesticide use or poor regulatory control. The recommendation is to understand the local risk. What is the agricultural landscape, aquaculture industry around the farm or the harvest area, and consider risk-based testing in known or suspected contamination zone. So if you evaluate the risk. The risk is high, consider testing for those pesticides as well. Moving on to radionucleotides in seaweed, they are naturally occurring and also can be as a consequences of nuclear power, weapon testing, and other phosphate and metal processing industry. And they accumulated from seaweed accumulated from contaminated water. And seaweed is usually actually used as a bioindicator for environmental radiation level. The control strategy for this is evaluate the harvest area near nuclear facilities or legacy contamination, test seaweed of risk if identified, and compare results to FDA-derived interventional levels, which is for the product that they don't actually have food safety level established. And then our persistent organic pollutants include our chlorinated biphenyls and also our PBDEs, an emerging flame retardant. They are highly persistent in an environment, accumulate in lipid-rich tissue, but seaweed can still accumulate them despite the low fat content. And the key finding is some kelp species and ova species have shown POP by accumulation, and species that they have rough surfaces trap more pollutant as well. Factor affecting POP accumulation again is a species differences. The one, as I said, that they have a different texture, accumulate this material more. And there is geographical variability. Some areas report low concentration. So monitoring of those areas is essential because they have a very long half-life. So when we are controlling chemical contaminants, we need to pay attention that many of these products are getting dried. And the literature says when you are like the contaminants can get, like the concentration can get 5 to 10 times higher. And as I said, but the dried seaweed is getting eaten in a small amount. Whenever we are doing the risk evaluation, we need to think about whether it's going to the vulnerable population. We can do the frequency check, or we can do some sort of calculation based off those that can help for risk consideration. And the control measure is usually understanding the harvest environment and targeted testing and testing of the product, although we understand that testing might not be the easiest way or most available way to everyone. So the control strategies that we are still debating on this a little bit. In our guidance document, we have provided 3 different control strategies for environmental chemical contaminants, including source control. We understand that usually when the waters get tested, it's not tested for these environmental chemical contaminants, but that's one of the methods that we suggest for now, or making sure controlling that supplier certification control, making sure that product is safe, tested, and is coming with some documentation showing that the product is safe. And the most reliable one is product testing to make sure that they don't have these environmental chemical contaminants. There are some research gap. We still don't know what is the relationship between the contamination in the water and how much is going to get accumulated in the seaweed. And we understand that microplastic and PFAS are one of the main like environmental chemical contaminants that people are talking about. But like other food stuff, the data is limited. So more research is needed in that area. As I said, most of the research on heavy metals are only total. So we need to do a speciation analysis to see which organic versus or inorganic is present or not. And there are limited longitudinal studies that capture seasonal and geographical variability in contaminant accumulation across time and location with seaweed. And also, there are limited research exists on the impact of processing. As you saw, we didn't put processing as a way to control the environmental chemical contaminants for seaweed. There are some evidence that you might be able to use some sort of fermentation or bleaching to reduce the environmental chemical contaminant. At the time, because the data is limited, we haven't included in the guide as a method to decrease environmental chemical contaminants. But in that case study that the FDA did, they suggested that if you can prove with validation method that your processing method has increased the amount of heavy metal, you can use that to control the heavy metal. But again, the data is very limited at this time. With that, I wanted to thank you for your attention, and sorry that I talked so fast. And
Right.
I'm gonna stop share and get any question you might have.
Thank you, Razieh. So feel free to raise your hand if you want to ask your question. There's a Q&A box or there's the chat. You can put them in there. While we're waiting for questions to come in, I will put my contact information back up as well as our evaluation, which I ask everyone to complete before you head out today. And also want to clarify something one of our co-authors pinged me on is just when I presented the iodine concentrations earlier, those were all dry weight in the dried seaweed product. And the example serving size where I kind of just gave you an idea of if you have this much iodine in a product, but your serving size is this size, this is actually how much an individual may be consuming. That was just an example. You need to assess what your final product is. Are you selling a dried product? Are you selling a wet product? And what's your serving size? Is it more than 5 grams, less than 5 grams? And assess the risk of iodine exposure based on those upper limits, based on that final product and the serving size you're choosing. All right, any questions? Again, you can put it in the chat, the Q&A, or raise your hand. Happy to answer to the best of our ability. And ideally, this guide will be out in September, and you'll get more clarification on the various recommendations and access to all that information. All right, question on labeling in other states. So the only one I know that has any specific labeling requirements, I believe, is Connecticut, which, well, it doesn't even require. It's actually a recommendation to label for crustaceans. But as far as that, I don't believe there's any other labeling requirements being enforced by any other states, but feel free. I know we have a lot of state agencies and regulators on the call. Feel free to chime in if that's not the case in your state. But I don't believe there's any labeling requirements.
Mike, can I make a comment about those?
Yep.
So FDA has this document that is reference amounts customarily consumed, and they have number for dry seaweed and seaweed powder. And in the document for cadmium, they suggested to use this when they were calculating things. So I'm going to put it in the chat for people to look at. I'm going to put that document about cadmium as well. I think it would be interesting to look at it. Again, we didn't provide any type of calculation like that in our guide.
And I see a question in there from Golson. I put a link to our evaluation in the chat too, if you don't have a smartphone or can't scan the QR code. So for practical solution for iodine removal. So I didn't necessarily go into detail on the practical solutions and the various methods. For the most part, it's going to be blanching or steam blanching, water blanching, water rinses, all showed promise as reducing iodine content. The water bath or water blanching was the most effective and had the biggest drop. Again, we're seeing 50 to 70%. In the guide, we reference the various resources that showed that, so you can look to them, but there aren't necessarily validated studies like this is what you do to reduce iodine to this extent, right? So the validation studies still need to be done for widely applicable use. Ultimately, right now, it's going to be up to the producer to assess their process and validate that it is actually effectively removing X amount of iodine from that product. Let's see. Contact from the Connecticut. Yes, Jessica, I can definitely get you in touch with folks from Connecticut. Although I will also add, I know Connecticut regulates seaweed a little bit different than, well, different from federally and different from here in New York. For those who missed the regulations webinar, I encourage you to go back, but seaweed falls under preventive controls for human foods rule. In Connecticut, they predated the designation of seaweed as a raw agricultural commodity in their seaweed regulatory framework, and they operate under the HACCP system and regulate under the HACCP rule. And so their regulation is a little bit different for seaweeds than here in New York and many other states and federally. All right, any other questions? All right, so again, please, before you jump off, be sure to take that evaluation. Give us some feedback on today's session or anything else you'd like to know. We can follow up and maybe we'll guide future sessions related to our seaweed work.